Hi guys, so in this video we're doing section 6.2 and we're going to look at differential forms of internal energy, enthalpy, Helmholtz energy, and Gibbs energy. So just to remind you of kind of what we know so far about these things. Internal energy, it's all of the energy in a system, kinetic and potential, and it's equal to Q plus W. Enthalpy is how much thermal energy flows into or out of a system at constant pressure, and it's equal to U plus PV. Helmholtz energy is the maximum amount of work, total work, PV and non-PV, that can be done by a system. And it's also a criterion for spontaneity at constant gives us a criterion at constant temperature and volume. And A is equal to U minus TS. Gibbs energy, G, gives us the maximum amount of non-expansion, non-PV work that can be done by a system, and also the criterion for spontaneity at constant temperature and pressure. And G is equal to H minus TS, which is also equivalent to U plus PV minus TS. So that's kind of where we're at now. Now, one thing we also know from before, this is chapter 5, we proved it back then, that du is equal to TdS minus PdV. Going down to enthalpy, okay, taking the differential of enthalpy, H is U plus PV, so dH is equal to du plus dPV, and substituting in place of du what we just got up here, TdS minus PdV, just plug that right in there, we get this. dH is TdS minus PdV, that's the du part, plus now the differential of dPV is PdV plus VdP. And when we do that, we see that the negative PdV and the positive PdV cancel, and we're just left with TdS plus VdP. So dH equals TdS plus VdP. Helmholtz energy is equal to U minus TS, so the differential is du minus dTs. Once more, substituting in place of the du we saw up here, we derived in chapter 5, TdS minus PdV. We get the du portion, and then the differential of dTs, which is TdS and SdT. And here, the TdS term and the minus TdS term cancel out, leaving us with dA equal to negative PdV minus SdT, or negative PdV plus SdT. Likewise, for Gibbs energy, G is equal to H minus TS, so dG is equal to dH minus dTs. Taking the dH term, replacing it with what we just got up here, TdS plus VdP, right there. And then the dTs is TdS and SdT. Here, once more, the TdS and minus TdS terms cancel, and we're left with dG is equal to VdP minus SdT. All right, we're going to do some good stuff with this, don't worry. So, next thing is, because these are state functions and consequently their differentials are exact differentials, we know this. This is this is from calculus, but we first used it, I think, in chapter 3. If we have a state function f of x and y, then we can write the total differential of f as df of xy is equal to partial f partial x constant y dx plus partial f partial y constant x dy. Applying this to our first equation that we showed on the previous slide, this guy right here. So what we're gonna do is we're gonna write out the differential of du, just like we did for f. And so u, the way we set it up, is a function of s entropy and v volume. So du, which is a function of s and v, is equal to partial u partial s constant v ds plus partial u partial v constant s dv. Now, we also know, okay, that the second equation is true, like we just showed you, du equals TdS minus PdV, because this term right here is equal to du, and this term here is equal to du. They're equal to each other. Not only that, because we have this ds right here and a term in front of it, and a ds here and a term in front of it, we know that this term here must be equal to this term here. So we can say, this is something useful, partial u partial s, the constant v, is equal to the temperature. Likewise, the term in front of the dv here partial u, partial v constant s, must be equal to the term in front of the dv here, minus p. So we get partial u, partial v constant s is equal to minus p. Now we can do that for all of these equations, writing out the differentials like we just did, and get relations like that. And when we do, we end up with these. So I'm not going to go through all those with you, but you definitely should make sure you can derive all of these just the way we did that first one. So this first line, that's what we just derived, and you should be able to get the rest of these too. Partial h, partial s, constant p is equal to t. Partial h with respect to p at constant s is equal to v. Partial a with respect to t at constant v is equal to negative s. Partial a with respect to v at constant t is equal to negative p. Partial g with respect to t at constant p is equal to negative s. And partial g with respect to p, constant t is equal to v. Now, we can do even better than that. We can derive what are called the Maxwell relations. And the way we do that is we use another property of state functions that it's from calculus, but once more we saw this back in chapter 3. And that is that if we have a function f of x and y that's a state function, then we know this must be true. Partial with respect to y of partial of f with respect to x to constant y, the whole thing at constant x, is equal to partial with respect to x of the partial of f with respect to y at constant x, whole thing at constant y. So if we apply that to the differential forms of these four state functions, we end up with this. And again, you should work that out on your own and make sure you can get these relationships, derive those. Notice we have, in this first row here, we have something, a partial with respect to v at constant s, constant entropy, right? And partial t with respect to p at constant entropy. So it's useful to keep in mind what it means for something to be at constant entropy, because ds is equal to d bar q reversible at constant t. If s is constant, that means ds is 0. Temperature can't be infinity, so that means that dq reversible must be 0. And what that means as a practical matter is that it's a reversible adiabatic process. Adiabatic because no thermal energy can flow into or out of the system. And that's what we have.